So far, we've looked at defining our own simple types. So we started with enumerative types. Those are types where we can just list all of the possible values. That was like our suits in a deck of cards. And then we've seen how we can build them up using type constructors to build more complex types like cards, and then ultimately a deck of cards. We've also seen how to define recursive types, and we use the natural numbers as an example for that, where a number is either 0 or it's a successor of 0. Today we're going to have a look at a recursive type, which is also parameterized by an abstract type. So what that means is we're going to define a type which holds another type, but that type is not instantiated until runtime or whenever someone calls it. So that could be, for example, if you had like list as a parameterized type because it's a list of A's. You don't know what that A is going to be, but at runtime someone gives you a list and then you know, okay, I'm working with integers now. So what we're going to look at today is a binary tree. Now a binary tree, as our definition says, is either a leaf containing no value or a node containing a value and two subtrees. Now there are other definitions of binary trees. Sometimes the leaves hold the values and the nodes just hold subtrees, but this is just the example we're going to be working with today. And we have an example, so we're given that this is what it should look like. So we've got a node, and then we've got a subtree. This will be another subtree here. We've got a value, and then we've got another subtree here containing another subtree. So this is what the type should look like when we're done with it. Now, how do we do this? Well, we're going to start with our usual. We're going to define the data, and we're going to say btree A. Now this A is the abstract type that won't be instantiated by us directly. We'll leave it generic for now, and that means that our type can be used in more cases. So this gives our code more flexibility, more genericness, and more power that way, because we don't instantiate this ourselves. But that A is not a parameter, it's a type. So you could think of that as being int, could be the card from the previous video, could be anything, but that's just an abstract type that will be instantiated later. Now, when you're looking at these questions, and you'll likely get a definition like this if you're asked to instantiate a type, what you want to look for is keywords. So in this one, the keyword is either. So when you see that either, you know that you're going to put something on one or either side of an or condition, because either the thing is a leaf or it's something else. What that means is we can just say, well, one case is a leaf, and that's that part done, because it's either going to be that or it's going to be something else. And you can see that leaf here doesn't involve anything else. We just leave it like that. So on the other side, it's or a node containing a value in two subtrees. And we know what these look like. They look like node, subtree, value, subtree. So let's say we have btree A. That's the recursive call, so that will build the subtree for me. And we have a value of type A. And we have another subtree A. So that is our definition, and that's how you just take these English descriptions and translate them directly into your code. You look for keywords like eithers, ors, and then just take the conditions out from there. Now, I'm going to say that this is deriving show, just so that we can print this to the terminal. And then we've got a couple more examples to show us how we'd work with this. So we've got our definition, and now we want to define some tree for a numerical tree. So how do we bind that? Well, we know that the type is going to be generic. However, this function does not have to be. This can only be applied to binary trees which contain a numeric type. So this is going to be num A, and that's going to take a binary tree of type A, and it's going to return something of type A. That A is an integer, a number, a float, whatever it is, it'll return something of that type. And then we can decide how we're going to work through this tree. Now, the way I would recommend doing this for these abstract types is when you're doing something simple like this, you can just read your cases off from the actual type declaration. So we know that one case is going to be when we have a leaf. We know that another case is going to be when we have a node. So those are the two cases we need to deal with off the bat, and that makes our pattern matching all the easier. So let's see how we do that in practice. Well, if I have a leaf, then I need to decide what to do. If I'm summing the values in a tree and I get to a leaf contains no value, I don't want to change the overall sum, so I should add 0. Remember, 0 is the identity for addition in the same way that 1 is the identity for multiplication. And then we have some tree. And now I need to do some pattern matching, which is maybe a wee bit more complicated because I have to give it something that looks like a node. But this isn't too bad. So we have a node, and then I have a subtree. Now, I don't really need to spell out what this subtree looks like because I'm going to recurse, but I can just give it a name. So I'm going to say this is the left tree, we have a value x, and then we have the right tree. So now I have variable names that I can pass to the recursion to recurse through the left tree and recurse through the right tree. Now this is possibly a bit more complicated than things we've seen before because you have to recurse down either side of the tree. You don't just recurse in one direction, you recurse in two, and then we will evaluate back up. But it's not too bad really, because what we're going to do is we're going to add x, since that's the value, to the recursion on some tree, left tree, and some tree, right tree. And that's it. So let's save that, and we'll reload this, and let's see if we can, God, always copying into terminal is a nightmare, but let's see if we can manage it. So some tree, and I'm going to paste this guy in here. I'll need to put some brackets around that actually. So if we look at the numbers in this tree, we should get 5 plus 5. So we should have 10 plus 6 plus 7. So that should be 23 if I'm doing my maths right. And there we go. So that's actually quite a simple way to manipulate this tree. But some tree is quite a simple operation. So let's do something a little bit more complicated. Now sometimes binary trees can be ordered in that there is some internal ordering scheme through which items are placed in. Not always, sometimes they can be used for other purposes, but sometimes they can be ordered like that. In fact, this one is ordered in a way. So we say define insert tree, which inserts a value into a tree. Assume smaller values should be stored on the left and larger values on the right. And you'll notice actually this tree is balanced in that aspect. So 5 is at the top, and then we have 5 to the left, and then the larger values have been put into the right. So this 7 goes to the right of the 5, and this 6 goes to the left of the 7 because it's smaller than the 7. If we had 8 in here, that should go to the right, and it would replace this leaf. So let's see how we do this, and this will be a bit more involved. Now, the tricky thing about this is if we, or not necessarily the tricky thing, but if we want to insert something, we need some idea of ordering. So we're going to need to restrict this to the ordering type class. I'm going to take a B tree type A. Actually, let's take a value of type A first, and then we'll take the B tree. And we're going to return a B tree A. Now this one will be a little bit more complicated because we need to retain the structure of the tree. So in the previous one it was quite easy because we could throw away all that structure. However, this will be a little bit harder. So let's see how we would do this. So let's start with the simplest case when we have to insert a value x into a leaf. Now, what do we do here? Well, we can't just put a value into a leaf. A leaf doesn't hold a value, that's part of our definition up above. So instead, we're going to have to change that leaf into a node, because a node can actually hold a value. Now let's say the value x goes here, and then figure out what we need to do. So a node, as we know, has to have two subtrees. But there is nothing lower than this leaf because we're at a leaf. So what goes in here? Well, really the only choice is to put a leaf here, because we have to satisfy the structure of a node, but we need to give it a value that makes sense. So putting leaves on either side of the new value would make some sense. So we don't want anything else to be lower than it yet. If we've gone to a leaf, that means this is as far as this one can go, and therefore we just need to create a new node. So let's do the next case, which is a bit more complicated, where we have a node, the left tree, value x, and a right tree. And what I'm going to suggest we do is use guards, because there are two cases here. I'm going to say that if something is lesser than or equal to it, we should go into the left subtree. And if the value is greater than, we go into the right subtree. So this might be a little bit of an odd definition in that if you have a value that is equal to the top value, you have to keep going down until you find a value lower than it, and then stick it there. So there are other ways you could define this, but this is what I'm going to go with now. So actually let's call this y, because that doesn't make sense. So we say if x is less than or equal to y, then we do something. Then what we're going to do is insert tree x into left tree. However, this isn't quite right, because this is just going to go down into the tree, but it's losing the structure that it's already got. So that's not what we want. What we want to say is this should be wrapped in a node, and the new left tree will be whatever is returned from inserting x into the left tree. and then we'll keep our value y, and we'll keep our right tree. So notice how with this type we have to be a little bit careful about retaining the structure of the overall thing. So we have to make sure this node is here, because otherwise we would lose part of the tree. We wouldn't be returning the right type anyway. So, and then the other case is where x is greater than y. You could of course use otherwise if you wanted, and we're going to do the same thing. We're going to say node, but in this case we insert into the right tree, because as we said, larger values should go to the right. So this should be left tree. We'll keep x, and we have insert tree into, or x into right tree. I keep forgetting that this should be y, not x. And there we go. So this is a little bit more complex as well. We have two cases where we either recurse one way or the other way, kind of similar to left tree, where we had to have two recursions going on at the same time. This is just part of the nature of binary trees. They're a little bit more complicated to work with than some of the types we've seen so far. But let's save this. We'll come in here and we'll reload it. And let's see if we can, so we've got our sum tree there. Let's change this to insert tree. And let's say I want to put a value of 1 in. Now that should go into here where this leaf is, because this is the leftmost subtree and this value is less than 5, so it will go down to here, then go into here. So let's see if that works. And indeed we get a new node where this leaf used to be, and that's worked as intended. So let's try that again, and let's say we want to put in a value of 8. So this should go into this subtree here because it's a larger value than 5. So we go into this node, and then it would say, okay, is it larger than 7? And it is, so it should go into this leaf. And indeed it does. So this is how you'd work with something that's parameterized by an abstract type. You can see that we can still define functions on it. We might need to restrict the types that we're working with to some sort of type class, but by allowing our types to have abstract values, we give them much more power, much more flexibility in how we can use them. So this binary tree could be used to, in theory, could be used to hold any kind of type. These A's could be lists, they could be other binary trees, it could be whatever you wanted, they could be a lot of things. But the point is to show you how you'd work with an abstract type, and how you would do some recursion examples with something that's a little bit more complicated than just say a list or something like that. But I hope you found this useful. That's everything we're going to cover here today. If you have any questions about any of this, or you found any of it tricky, please do feel free to get in touch. Thanks.